Hi, welcome to another lecture on Calculus 3. Today we are going to talk about vector valued functions. Let's go explore this topic together. Vector valued functions in 2D or 3D are essentially curves in the space that we are considering. So if you have, for example, a parabola in XY coordinate system, that is essentially showing a vector valued function. In 3 dimensions, similarly, any curve is a representation of a vector valued function. So uh, typically two formats are used to talk about these type of functions. In 2D, we can put the two, these are called scalar functions, in brackets, and that's going to be representation of a vector valued function in 2 dimensions. Another style of writing the same thing is to write the x coordinate times I and a y coordinate times j, and I and j are the unit vectors in the x and y axis. In 3D we simply have one additional piece, and so if the components are f, g, and h, R can be written in this style, or as f of t times I plus g of t times j plus h of t times k, where I, j, k are the unit vectors in direction of x, y, and z. Best way to learn this is to practice a few examples. So let's start by a basic case. Suppose we ask that we sketch a curve given by r is equal to, say, cosine of t and sine of t, or perhaps it is given as cosine of t. Now I'm not going to be coloring this thing for you any longer, it takes too long, so I just write it like that, and it's assumed that its I and j are unit vectors. I might also drop the arrow on top of r just so that we simplify our writing. Of course, you notice in the textbooks they write this thing with a bold font, and that automatically tells you that they are dealing with a vector. But of course, with handwriting, that also takes quite a bit of time. So from the context, you have to know what each letter represents. So if we are doing this thing by hand, we might as well make a table. So we might make a table t and then x and a y. T typically belongs to some kind of an interval, or you might infer what the interval might be. So for example, a natural interval to consider is from 0 to 2 pi, or whatever you might have in mind. So let's start at point 0. Of course, at point 0 cosine is 1, so x is 1 and sine is 0, so this is going to be 0. So by now what we have at the very start is that we are at the location 1 and 0. So suppose this is 1, this is point 1 and 0. Let's jump to the next time interval, say pi over 2. At pi over 2 cosine will be 0, sine will be 1. It means I'll be at this location. So at this point with t was 0, now t is equal to pi over 2. We are at the location 0, 1. And of course, if you go to time pi, cosine has become minus 1, while sine is 0, and we have arrived at this point. So there's a point with the coordinates minus 1 and 0, and time is now pi. Finally, if we come to 3 pi over 2, we are at 0 minus 1, so we'll be at this location. That is the point 0 minus 1. T is equal to 3 pi over 2, and that's the location at that point. Finally, if we arrive at the point 2 pi, we are back to 1 and 0, so we are back to this location. So of course, if we fill in for more time values, we are just traveling on a circle, and I progress is tabulated against time. So at different times we are at this point, different points of this circle. So the story is similar for any other curve in 2 or 3 dimensions. It could be more complicated, but the idea is that you're tabulating position versus time. Sometimes we want to have the curve represented, we call this a parametric representation. So sometimes it's possible to go to an ordinary equation for the curve. So in this case, x is cosine of t, y is sine of t, and of course we notice that x squared plus y squared is equal to 1. So that is a curve, and that this is an equation whose snapshot is just that parametric curve. Sometimes we want to go in reverse, that is, we want to start from here and go backward to what we had. And the simplest, there are many ways of doing this thing, that is, from a curve going back to the parametrization, you have many choices. Let's take a look at an example. Suppose I have some arbitrary function, and what we want to do is to write as a parametric curve, or as a vector valued function. So one might be searching for a kind of a parametrization that would be very nice and having lots of many properties, but that is not necessary all the time. So for example, if I take x to be t, y simply is t squared plus t cubed, and I can say r written as t in t squared plus t cubed is a parametrization of our curve. Of course, you could have put anything else here, and then we would have a different expression here, and that would be just as good as a parametrization. But there are other fine points to consider, but for now that would serve our purposes. Here's another example. Higher level question here is sometimes when you have several like two surfaces in 3 dimension, when you intersect them you get a curve, and many times we are interested in a representation or a parametric form of that curve. So here's a question: find the intersection of y is equal to x squared and x squared plus y squared plus z squared is, say, equal to 2. Now I chose two simple surfaces. This one immediately reminds you of a very familiar surface. What surface is that? X squared plus y squared plus z squared equal to 2. Who's that? This is, of course, a sphere. How about this one? Y equal to x squared. That might maybe you have forgotten by now, but what did we say about equations where one variable is missing? Y equal to x squared. What kind of surface is that? So of course there is no z here. Y equal to x squared by itself would be a parabola on an xy plane, but if you stretch it in the direction of the z-axis you get a cylinder. So this is a special kind of a cylinder. You might attempt to see what's happening here by hand first. X, y, z. So y equal to x squared, we have seen this thing scenario several times. It is some surface that's a cylinder. So to represent it, you want to perhaps do something like this. So this is the y equal to x squared surface. How about the other one? The other one is a sphere, so that sphere is going to be harder to. Well, these two surfaces are going to intersect each other. Obviously, some parts of this cylinder are inside the sphere, some parts are outside. It's a single piece, so they are going to intersect each other on the on some curve. The question is, what is that curve? How can we show it? How can we parametrize it? Very easy. Suppose you say, well, x, let's take x to be our parameter t, and obviously from here we see that y will be t squared, and if we take these two and plug it here, we see that, well, x squared will be t squared, and then y squared will be t squared squared, and z is now our missing quantity, so I can figure out that the z squared is going to be 2 minus t squared minus t to the 4. So z here is going to be either plus or minus say 2 minus t squared minus t to the 4. Let's focus on the half that is on the upper half space. So if we assume that z is positive, we are going to concentrate on the half that is up here. So my parametrization of this curve is going to be something like this. T is the first component, t squared the second component, and with the assumption that we are taking the upper half of this thing, that's going to have the following formulation in it. Now when we write this type of vector valued function, all the issues that we learned in pre-calculus and calculus are applicable. The issue of domain, the issue of continuity, derivatives, and so on, all of them exactly word by word translate here. So for example, if you want to deal the issue of the domain here, well, there's no problem here, no problem here. Here I have a square root, and the radicand has to be positive for me to label it as z squared. So what do I need to do? I need to make sure that 2 minus t squared minus t to the power of 4 is a positive quantity, or at least it's 0. Here's another way of writing it, a little bit more familiar to our eyes. This quantity has to be then therefore negative. I just multiplied both sides by a negative. Well, I can go ahead and factor this thing as t squared plus what's that, t squared plus 2 times t squared minus 1 has to be negative. Well, this t squared plus 2 is always positive because they are sum of two positive quantities, so I want t squared minus 1 to be less than or equal to 0, or t squared has to be less than or equal to 1, and therefore t has to be less than or equal to 1 and larger than equal to minus 1. So something like this will be considered the domain of our function. Our vector valued function here has a domain which tells you the t in absolute value is less than 1. Now we can attempt to graph these things, but gradually our problems are going to become harder and harder. So one more help from our favorite software here. Let's go ahead. So I have typed this equation as an implicit surface. So when you go want to add something to your graph, you have lots of choices. For example, you can go an implicit surface, and implicit surface you can put x and y, z in any kind of combination. That's going to be your surface. That's great. Then we want to have a curve, uh, well, that curve comes as the intersection of two of these surfaces. So one of them is y equal to x squared, and the other one is well, they are a sphere. And this one we said is the cylinder that looks like a page has been kind of bent. Now we see an intersection here, is that right? We see an intersection on this these two surfaces. It kind of looks jagged again because of the issue of how many grid lines you allocate. So on fast computers you can increase this number and make the picture be less pixelated, but again for my purposes I just keep the numbers low so that my computer doesn't slow down. Well, the intersection of these two, we can visually see what it is, but as a formula, how about the formula? This is the formula we just had in the previous page. X was labeled as t, y, which was equal to x squared, was t squared, and then z, we calculated the z out of this, and that was this formula. So I've just typed that formula here. How did I bring this up? So when you go select a curve to be included, so you have a space curve that you want to graph, and that's what we are doing. We have selected that and then fill it up ourselves. So if I turn this curve on, you see that curve showed up here, and there's another half of it is on the back side. You even can see a point moving on the curve, so that's a trace. It's called a trace. So I hope everybody can see that point, and you can control a variety of properties of that point. So up to here at 0 it reaches that high point, and the other half of it is in the back of the picture, so you're not seeing it. So to turn the trace on, you just turn on this curve settings, and so I have turned it just to trace. Later on we are going to learn about other stuff like vectors, trace vectors, velocity, acceleration, and many other things interesting, more advanced. But for now, so what do we mean by parametric representation of intersection of two surfaces? Well, just like what you see here, two items intersect each other in space, and we attempt to find the formula for that intersection. Let's go ahead and just finish by some small remarks about one of the very basic and also very interesting problems that you have seen probably since I would say pre-calculus, but it's a good idea to look at it again. Sometimes we want to go from point A to B. Of course, we have many choices on how to go from one place to other place. All of those choices represent themselves in a parametrization that you choose. Well, most normal thing to do is to go on a straight line and go at a constant speed and so on, but of course you could have gone in all sorts of directions and all sorts of speeds and such. Let's go after the simplest. So we are after a way of representing a curve that starts at A and goes to B in the most straightforward, simplest fashion. This depends on a very basic problem from pre-calculus. Suppose I ask you to find a function that does the following. Suppose I have as t-axis, t representing time, x representing a location on an axis, and I want to go from location x1 to location x2 when the time runs from 0 to 1. Okay, I want to go from location x1 to location x2. Well, that most basic way of going from this to that one is to go on this straight line. Is that right? So what's the equation of that straight line? That straight line has an intercept which is x1, has a slope which is a difference of these two over a difference of these two. So it is x2 minus x1, that's how much x is gained, times over 1 minus 0, which is just 1, times t. So this is the simplest function that starts at x1 and goes to x2, while t goes from 0 to 1. There's another way of writing this thing, which is to write x1 plus x2t minus x1t, and bring x1s next to each other and write it as x1 times 1 minus t plus x2 times t. This is the same as that formula. Now if you are in 2 or 3 dimensions, A has coordinates, B has coordinates, and to go from A to B we follow the same formalism. So I'll say if I want to find a location R, then I start at the location of the point A plus the difference of the 2 locations times t. This will be a formula that's going to tell me how to start at the point A. When t is 0, this whole thing becomes 0. I'll be at the location A. That will be RA. When t is equal to 1, this becomes RB minus RA. And then you add RA to it, you'll be at the location B. And that is how to reach the point B. So suppose, for example, A has coordinates 1, 2, 3, and B has coordinates, just to keep it straight, 10, 20, and 30, and I want to write a parametric function that starts at A and goes to B. So what do? I say 1, 2, 3, that's the starting point, plus difference of these two. Difference of these two is going to be 9 and 18 and 27. Difference of the two starting and ending position times the time t. So if you want to add them up, it's going to be 1 plus 9t, 2 plus 18t, and 3 plus 27t. Let's check this thing. When time is 0, well, all these portions disappear and we are at the location 1, 2, 3. That's our starting point. When time is 1, this becomes 10, this becomes 20, this becomes 30. We have reached the location B. So to go from one point to another point in a unit of time on a straight line, and the formula would be something like what we just wrote here. So you are going to use that in several problems that are going to show up in this section. Okay, so this was a short introduction to vector valued functions, and then we are going to go up to more advanced issues. Just whatever we study with the functions in calculus, those items are going to come up. For example, differentiation, integration, and various properties of trajectories that we are going to look at in future lectures. Until then, good luck and God bless.